There are two prerequisite experiments we conducted before conducting our speed of sound experiments. Firstly, we made a makeshift ruler using a roll of tape. Using 5-Fox's acoustic timer, we used a marble and dropped it from the top of a roll of tape and measured the time it took to reach the bottom of the roll of tape. After multiple trials, we took the average time and used d equals 1/2 at squared to determine the experimental diameter of the roll of tape. From there, the circumference was calculated, deeming each full rotation of the tape to be roughly 0.449 meters long. The experiments shown later in this video all use this makeshift ruler to measure out the distances and the lengths that are being used in each experiment. All of our following experiments were done in a room with a relatively consistent temperature, which was measured using the following procedure. First, we filled 2 translucent tubs of water and filled one with ice to lower the water temperature to 0 degrees Celsius, 0 degrees Celsius being water's melt freeze point. We let these 2 tubs sit for a period of time so that the temperature adjusts to the room as well as becomes 0 degrees Celsius. We determined that the water with the ice was at 0 degrees Celsius when there was no noticeable change to the ice over a span of 3 minutes. Next, placing a strip of tape on the sides of both containers, we marked the initial water levels in the tubs. Following this, we filled a balloon with air, tied it closed, and proceeded to submerge it in the tub with the 0 degrees temperature water. We held it in such a position to allow the air inside to cool. We then marked the new water level and repeated the step of submerging the balloon and marking the new water levels in the tub filled with room temperature water. Then, by measuring the dimensions of the tub with the makeshift ruler as previously mentioned, as well as the change in water levels, we applied the relationship equation for the volume and temperature of gas, which is temperature final divided by volume final equals temperature initial divided by volume initial, which can be rearranged as shown right here. This equation gives us the temperature for the room temperature water. The final value of the temperature would have had some uncertainty due to the uncertainty in the measurements of the dimensions, as well as the temperature of both of the tubs. The following table includes our measurements and calculations, as shown here.
In this method to calculate the speed of sound, the acoustic stopwatch function in 5-Fox is utilized to measure the time it takes for sound to travel a measured distance. Then, using the velocity equation, velocity equals displacement over time, the velocity or speed of sound can be calculated. The data will then be adjusted to equal speed of sound in 0 degrees Celsius temperature using the 0.6 meters per second sound increase equation. These equations will be the primary physics principles used. The distances between the 2 cell phones and the time between when both stopwatches are started and ended is measured. For materials, 2 phones with 5-Fox downloaded will be used, as well as an aforementioned self-created ruler and optionally taped to measure specified distances. The data was recorded in a table format that outlined the steps of calculation to achieve the final value.
For the procedure, choose a location that has minimal background noise and have each person hold a phone. Having both people and cell phones a measured distance away, using a self-created ruler to measure the distances between phones, start both acoustic stopwatches by creating a loud noise at the first phone, e.g. clapping. While both phones are measuring the passing time, stop the phones by creating a loud noise at the second phone. Repeat this process for various different distances, recording the distance and the difference in times on the stopwatches for each of the trials. You may want to keep in mind that a louder sound will be required for longer distances. Next, to minimize sources of error, try to adjust the settings of the acoustic stopwatch such that the threshold and minimum delay are appropriate. The difference between the times can be first divided by 2, first phone time minus second phone time over 2. This difference must be halved because the first phone was started a period of time earlier, the time for sound to travel the distance, and was also stopped that same period of time later than the first phone. The distance and the halved difference in times can then be inputted into the velocity equation. Velocity equals distance over time to find the speed of sound. The data from these various trials can also be used to find the average value of the speed of sound and the experimental uncertainty. This calculation of velocity can then be adjusted to find the speed of sound in 0 degrees temperature by subtracting 0.6 meters per second for every degree above 0 degrees, as this is a known speed of sound behavior equation. The final speed of sound in 0 degrees Celsius temperature was found by averaging all the trial values. The uncertainty for this average was calculated by dividing the range of the values by 2 times the root of the number of experiments overall. Some sources of error included the uncertainty in the distance and the accuracy of the acoustic stopwatch.
Hello, today we will be using 3 phones and a remote control car to determine the speed of sound. This will be done with the formula for the Doppler effect, which states that the observed frequency of sound is equal to the actual frequency of sound waves multiplied by the velocity of sound plus the velocity of the observer divided by the velocity of sound plus the velocity of the source of the sound. And in the beginning, for the first part of the experiment, you will need two phones that are attached onto the remote control car, and you will also need to have one of the phones use the GPS location sensor, and this is to measure the velocity of the remote control car. So to do this, the other phone is just acting as a mass, so that the mass on top of the remote control car remains constant throughout all the parts of the experiment. Next, you're going to turn on the GPS sensor while it's on the remote control car. While picking up the remote control car, turn it on max speed. Afterwards, you're going to drop the remote control car onto the ground so that there's no acceleration. And after that, stop the GPS sensor and average the velocity of the car. In part 2, the phone that was previously doing nothing on top of the cart will be used to generate a specific tone of a specific frequency using the tone generator in Firefox. The other phone that was used to determine location and speed will now be used to determine the frequency of both the tone generated and the frequency of the car as it is rolling on the ground. On top of that, you'll also need another phone that is some distance away from the remote control car. And this phone will also be using the Doppler effect sensor. Activate the tone generator on the phone on the remote control car, and after that turn on the Doppler effect sensor for both of the other phones. And just like before, pick up the cart and turn it onto its maximum speed and then drop it onto the ground so that there is no acceleration. You're going to drive this remote control car towards the phone that is using the Doppler effect sensor. Here's the data gathered from our experiment. Using this data, we determined the speed of sound to be approximately 357 meters per second. So after adjusting for the speed of sound based on the temperature we observed using the experiment mentioned before, our experiment had a percentage error of approximately 3.4%. This could have arisen from a few sources of error. The measured values were the frequency generated, frequency observed, and the speed of the source of the sound. Both the frequency observed and the frequency generated were fairly consistent and only deviated by a slight factor compared to their magnitude. The velocity of the source of the sound, however, deviated greatly and was likely the largest source of error in this experiment.
We'll need an acoustic stopwatch, a coin, a ruler, and a stick at about 1.5 meters long. Okay, so now I'll be starting the acoustic stopwatch, and I'm placing it, you can't see everything in the frame, right in between, right in the middle, whoops. Then, placing the coin on top of the pole, and it times the difference between the first sound of me hitting the coin with the ruler to when the coin hits the ground. Then you place the phone with the light sensor beside the lamp, and the phone with an acoustic stopwatch at a distance the length of the stick away from the lamp. Start both timers at the same time, and when you turn on the light, when it clicks, it starts both timers. And then bring both phones together and turn it off. The click and the light should turn both timers off. Find the speed of sound. Take the time difference between the two timers and the distance of the stick that was measured in the experiment earlier. Divide the distance by the time and you will find the speed of sound.
This is the Sonar method for determining the experimental value of the speed of sound at 0 degrees Celsius. The following physics concepts and principles are used in this lab: echolocation, reflection, properties of waves, and kinematics. The materials needed for this lab are some sort of insulating contraption, a roll of tape, a good sound reflector such as a sheet of metal, 2 phones, and the Firefox app. We will be using the acoustic stopwatch and the sonar functions. The points of data being collected are the time intervals that Firefox displays, as well as the distance between the insulating contraption consisting of the 2 phones and the sound reflector. So how exactly does this work? With one side of the contraption open and all other sides closed off, essentially one phone will let off a sonar beep, which starts the timer on the second phone. The sound waves exit the open side of the contraption, reflect off of the sound reflector, and return for the second phone where the timer is then stopped. Make sure this experiment is done in a very quiet place. This is the Excel sheet where all our data is input into. As shown, we performed 17 trials, 3 of which were omitted due to placement reasons. Using the distance and the time, we can calculate the speed of sound using the equation v equals d over t, which gives us the preliminary speed of sound that is around 4.76 meters per second. To calculate uncertainty, we took the maximum value and the minimum value, divided it by the number of trials we did, and from there calculated the value, which comes out to be around 0.29 meters per second. All in all, for this lab, we ended up with a value of 4.76 meters per second plus or minus 0.29 meters per second as our experimental value of the speed of sound at 0 degrees Celsius.